Hello, scholars, and welcome to Summer Academy Geometry. I'm Mr. Harvey Sniffen III. I'm going to be your geometry teacher for this summer. Thank you for joining me today and for the next 3 weeks. We're going to be trying to go over some general concepts in geometry, but really what I want to press upon all of you is not just kind of how to grind through questions and do algebra associated with these concepts, these figures, these solids, and the like. What I want to do is kind of give you a background of what geometry is, how I appreciate it, how it relates to me, and kind of show you the skills that you can take and move on into your next algebra class with. That means that we're still going to be doing geometric concepts like thinking about parallelism or figures which are perpendicular and the like, but we're going to try and see how the art or the beauty comes out of that. Like how does understanding geometry generate kind of real world experiences? What I'd first like to do is give you a little bit of information in terms of how this video is going to play out, how our class is going to be structured, and I want to give you a historical background of geometry and kind of where a lot of this information comes from so we can get a nice, strong, refreshed base. At the end of the video, also what I'm going to do is explain some concepts or explain how we're going to be doing our online portion of our course for this summer, but we'll touch on that at the end. First off, what I'd like for you to do is grab a piece of paper, grab some notes, because the video that we're going to be going over is going to have some interesting concepts associated with it. And what we're going to be doing is, as we watch this YouTube video, which most of you will be interacting with on Edpuzzle, what I'd like for you to do is at the end of the video is answer a question for me. And what I would like for you to do is describe 3 things that you kind of found interesting or new. But more importantly, at the end, what I would also like for you to comment on is something that's or something or some way that I personally explained some of this information to you that's made you kind of view geometry slightly different. For me, as a background in history, as someone that has like a social science background, I find geometry really interesting because it allows you to create systematic approaches to things. Systems within history or economics or within the field of math are very powerful, and being able to articulate geometric systems in the actual real world gives you the advantage over a lot of people. And it's not with just like building bookcases or shelves and things like that and organizing it, but able to take some of these what we would call like binomial reasons, like being able to say something is a yes or a no statement, allows us to kind of create means of categorizing our own environment. It's cool stuff. We'll talk about it throughout the next 3 weeks, but I want to show you some cool stuff first. In terms of a history of geometry, we really have to kind of start back with the beginning of human civilization in many ways. You've seen like in your world history classes and the like, you have people starting as hunter and gatherers and eventually moving on to agricultural societies, being able to domesticate animals, being able to actually plant crops, grow them on a yearly cycle. Early humans were very agricultural based. They were stuck in certain particular areas. If they're going to be farming, they need to be near water and the like. But a lot of this has to do, interesting enough, with geometry or the way mathematicians were able to kind of calculate kind of early human understanding of their society and their surroundings. If you want to define geometry, kind of give it a loose definition, we can describe it as a collection of empirical principles, rules, systems concerning the calculation of figures or shapes and their positionality in relation to other figures. So we're talking about being able to calculate the size of something and relating it physically to other figures that exist around it. Essentially, geometry allows us to basically calculate the physical dimensions around us, our length and width, our height, as well as things like time, our 4th dimension as well too. In terms of history, though, geometry, like we have to really start all the way back. It's partially like the early mathematics of human civilization. The earliest known written geometric equation that's been found was about in the year 2000 BCE, all the way back in Egypt, and slightly around that same time in Babylonia as well too. So we found various artifacts dating from this time period, allowing people to kind of calculate different shapes and sizes. And there's a reason why we see this math dating back so far. If we're talking about calculating the physical things around us, obviously it's important to know how everything interacts and budges and nudges into one another. But geometry has two unique attributes to it that we'll start off first. The first thing with geometry, and we think about how you were probably introduced to it with this notion of a point, it's a zero-dimensional figure or a line. Geometry allows you basically to calculate distances. Distances seems kind of rudimentary, but to understand the distance between two objects allows you to calculate and figure out a lot of different things. When we're talking about calculating distance in a logical sense, we're talking about distance as something that's equal to time and theoretically cost. If we can go ahead and say that me, Mr. Sniffen, is on, say, like 50th Street, and I need to get to, say, 125th Street, can do algebra and say, okay, we're going like somewhere around 75 blocks. But if we have an actual numerical value to that distance, and we apply something like time, we get speed. And speed has a lot to do with logistics. We're talking about delivering things, we're talking about companies managing packages and things like that. You don't need to know just how far you need to travel to get to, say, to Albany, to state capital. You also want to know how much time it takes as well too. When we compare time and distance, we end up getting speed, and that's where we can start to assign things like, I'm going to have to rest in between going there. I'm going to have to refuel. I have all these different systems of influences that's going to dictate how I'm going to be able to relate the positionality of these two figures. When we have the ability to measure single distances, say like a one-dimensional figure, we can actually turn that into two-dimensional reasoning as well. So besides just measuring going downtown, I can also go west. Now we have two dimensions. We have like a width and a length. And now we have the basis of kind of geometric reasoning. We have two-dimensional spaces. Later on, of course, we saw things with like volume when we talk about three-dimensional spaces. But once we have the ability, or once humans have the tangible ability, the first time ever, to go ahead and calculate distances between different places, you get a tangible sense of positionality in the world. You're no longer just an individual sitting in a particular spot. You're no longer just a farmer in one particular location, but you have the ability to know that cultures exist in other places and how they relate to you. How close is that bad guy going to come and invade us? How close is the marketplace for me to actually deliver the goods that I'm trying to sell? If it's a certain distance, I know how far related in a relatable sense, how my pack animal might be able to travel, how far I can personally travel, what type of food I'm going to need to bring, what type of rations, and how much water am I going to need, because I can count everything out. If it's a place I've never been to before, having a notion of distance, having this ability to calculate time, gives me the ability to predict what's going to happen to me. And that's something that's very powerful that humans can do. We have the ability to look at patterns and pontificate, think of additional ideas, and predict what's going to happen into the future. We don't just walk into a room and then do, oh, what am I going to do next? We walked into the room and we had a specific idea or intent going into there. Once you have this ability to kind of create markings and indications, basically what you have is mapping. Without geometry, there's no such thing as mapping. Without geometry, there's no ability to dictate the coastline. There's no way to organize and plan your city. There's no way to really kind of have these rudimentary building blocks that all of our societies need. We can't we can't function with our roads. We can't function in spreading out our commerce. We need this ability to measure just singular distances and relate them to other objects on our experience in our life. Once we have this ability to create maps, we have a numismatic way, numismatic meaning like numerical or number-based way, of organizing different portions of our society. As I mentioned before, we're talking about early agricultural humanity. We're talking about people that are primarily dependent upon farming. We don't necessarily have hugely complex societies where we have the ability yet to have astrophysicists and various complicated job-specific titles. We have mostly people working with some type of craft skills, some type of farming. Once we have these data points, though, we can actually make maps. We can tell that farmer exactly where their land is. That having maps and the ability to kind of calculate how much space you own also allows for things like taxes. It allows for us to have city-states with much more complicated structures. And that's kind of what geometry is offering these early people, is the ability to look at their surrounding, calculate it, and then dictate future possibilities with it. Considering that most of these societies are designed around agriculture and trade, we really need this ability to kind of see where we can move our markets to, see where we can move our goods to. But there's a problem, though, here that comes up. There's a problem. As I mentioned, geometry has like these two specific unique factors when we're talking about early human civilization. We have the ability to measure distances. We have this positionality that gets created. But whenever we give directions, though, there's another thing that's there. Like if we're going to go ahead and like open up Google Maps, for instance, and we want to see how to get to school, for instance, today, or how we're going to get, to Six Flags in, say, New Jersey. We don't want to know just the left and the rights and which highways and entrance ramps to get on. We want to know how long it's going to take us. And that word long is interesting. When we think of length, we're thinking of a measuring distance. But when we think of something, how long it takes, we're talking about quantifying time. And time is something we take for granted. It's like the watch on our wrist. It's the alarm clock that goes off on our cell phone. But the ability to actually calculate time has really powerful connotations. Time gives us, mentioned before, it allows us to dictate speed in a sense. Mathematicians or physicists would call time the fourth dimension in terms of our universe and its complexity. Our first three being that physical length, width, and height. But time comes about as the fourth dimension. Time allows us to kind of calculate experiences and the world around us, not in just one moment, but in the past and in the future as well too. But how does geometry actually help us calculate time? Normally, geometry allows us to figure out, how large a coffee cup is, or the volume of a baseball versus a football. But how do we figure out time? Like, time is untangible. It exists, but it also doesn't exist. It's kind of like this human abstract notion, but it is there because things change over time. It's just a rudimentary word. But how, we know today we have minutes and we have seconds. We know how those two things relate. We know how many minutes are in an hour, how many hours are in a day, how many days are in a year. We're in a post-discovery world. We take these things for granted. We know the Earth goes around the sun. We know that it takes about 365-ish days to go around. We know we have things like leap year. But how do people that are just learning basic math, basic fundamental math, calculate all of that, though? It seems odd. We have to think about the people that needed this material. We have to think about life in a different way. One thing that's kind of unique from this time period, or say it realistically it's common throughout history, is that during the nighttime you look up and you see stars. We don't see stars in New York City. We don't see stars in most cities across the world because of light pollution. Even where I grew up, say an hour outside of New York City, you look up, you maybe see 30 stars versus 2 stars, or 0 stars, or mostly airplanes like we would in New York City. But when the ancient Babylonians, ancient Egyptians, and Sumerians were kind of beginning the organizational period of their society, they were way into what we call astrotheology. Astrotheology is basically like the study of the stars, and you apply a religious or cultural meaning to it, and you have basically what we in contemporary society called astrology, but for them it was their way of existence. It meant everything in most cases. You look up into the stars in the sky, and it is the most beautiful thing you can see. It's something that we don't have a tangible relationship to today. I would just say that one of my favorite things as I drove around the country with friends and things like that is once you get into the middle of the country and you look up in the middle of the night, it's stars, it's blackness. It shows you really that infinite size that the galaxy is. It shows you just how small you are. But how does that tell you time though? Seems weird. Like, how would looking at stars, burning balls of fire out in outer space, tell you what time it is like your cell phone can? It's all about this concept of positionality, though. Mentioned positionality allows us to dictate how close objects are on Earth, but you also have positionality gets generated with the stars because of consistency. And I'll explain how this kind of functions for you. I find it fascinating. When we're talking about the stars in the sky, when we're talking about how we see all this material in the air, we're talking about being on a planet floating through outer space, right? We're talking about a planet floating through outer space going around the sun. We're talking about being on a planet floating through outer space going around a ball of fire that's infinitely expanding. We have billions of stars that we can see. But how do you create systems around that? It seems like there's so much variation. What's kind of cool is that for these people, and you can see this today if you go out to Nebraska, say, or upstate New York, Vermont, is when you look up at the sky, it looks pretty much the same all the time. It's kind of hard to tell when things change. From day to day, when you look up at the stars, you will tend to see the same exact patterns, those almost astrology-like patterns, or what the ancient Greeks use, like Orion's belt, or Saturn, nebula. All these cool mythical names were applied to stars. They had these really strong religious connotations, but these really real-world tangible things. If an event occurred when a certain star system was up, it had a reflection upon your experience. Possibly the next time you saw that star system up again, maybe that pattern will occur. Almost say like the full moon and crazy events going on. But on a daily basis, the stars look pretty much the same every single day. They're there. But if you look really closely, that the patterns that are there, they stay the same size. The position between them, the figures, the shapes that they generate, stay basically consistent, where you can take a ruler and look up there and kind of measure everything out and apply some geometric reasoning to them, some shape equations, if you will. But over time, they kind of fade away. They disappear. As the Earth rotates around the sun, because of our axis, we see different stars as we point out, and we look at different places in space in this three-dimensional floating Milky Way that we live in. What these individuals were able to do is take a look and see those patterns and show consistency between them. They knew that if they kept looking, eventually that pattern that was over here that they saw in March 14th fades away as they begin to look at this direction in the outer space, and particularly as they're on the other side of the sun looking at the exact opposite side, they can't see Orion's belt anymore. But they do know eventually if they keep looking, and all they got to do at night is not get eaten, and hang out and socialize. So eventually when they get back over here, those humans that had that strong patternistic ability, they're able to see that star pattern appear once more. And that is where we get this positionality. We have a notion of time. As people chart it year after year after year, eventually those patterns, those stories that they could apply, appear in their reality once again. And here's where we can kind of combine these two notions of early geometry and how fundamental it was towards the early human experience. So we can see how early humans were able to go ahead and say, this is how long something took. It took 365-ish days or so for my pattern to reappear again in the same exact position in the sky. One thing to remember is that as you begin to see Orion's belt again, it's going to change its portion in the horizon, but eventually it'll be nice and high or so in the sky. And it's about 365 days until it's directly in the same exact spot. So that's one way that we can go ahead about using this notion of positionality and time to kind of relate this fielded geometry to our understanding of our surroundings. But how does that now go backwards and allow us to do that time calculation that we are more familiar with? Not measuring things in year cycles or seasonal cycles, which would be important to farmers, but how do we kind of bring it back to today? How do we calculate the individual days that appear? Some of you may be familiar with images like this, but we have what's called a sundial or a shadow clock. Shadow clock is an object, or sundial is an object that basically just uses like a stick and allows the sun to hit it and create a shadow. That shadow, we can go ahead and calculate out using typically like our triangle formulas. We can measure the lengths using Pythagoras' theorem because we have strong sticks pointing straight up, perpendicular shadow going out. We can use that notion of a squared plus b squared and figure everything out. So that's cool. We get that. How does it relate every single day though? What we're able to do is if we take this measurement, calculate it over that 365 days, we can chart out exactly how long that shadow appears, and that number that gets generated dictates what specific day we have. So as long as we're going to be using the shadow clock or sundial in the same exact location, and we're measuring at kind of like the same exact time, which usually we do with the sun going all the way in the sky, our noon time. From there, we can go ahead and create formulas that allow us to build and kind of see this idea or this concept of time throughout the day. One thing that ends up getting generated from here, though, is there was a lot of confusion during this time period. People had their sundials, or say a consistent sundial. They all had a 6-foot-tall sundial, but they end up getting different calculations in different places. From my explanation, I can show how you can get as long as we're using the same location, it's going to be the same shadow. It's 365 days, Earth goes around. We know the sun's in the same exact spot, because we know star patterns are in the same exact spot. We have the same exact shadow all the time, 365 days. What ends up happening, though, is that as you go north and south along the planet, away from our equator, we end up finding out that the Earth is curved. So early humans knew for a fact that we had a curved Earth way, 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 way before this notion of Christopher Columbus sailing the ocean blue and trying not to fall off. It's common knowledge, particularly within Greek cultures at this time, Egyptian cultures at this time. They found that the Earth was essentially like an oblong spheroid. It had this notion of a curve. As you got farther up to the top or farther away from your original point, the shadow changed. And that's because the Earth is slightly farther away. They were able to kind of go ahead and wrap their minds around all this and all these different positions and create systems that allow them to dictate exactly just not a 2D map, but almost a 3-dimensional map. We're talking hundreds and hundreds of years, over 1,000 years before Galileo, people creating equations that actually dictated almost the exact size of the Earth prior to any satellite coming about and measuring anything, prior to any computer coming about and going ahead and calculating it out. It's pretty magical what these people were able to do. And for me, that's kind of what reflects a lot upon me with geometry, is we can take rudimentary things like just strict measurements, and as long as we're comparing, contrasting those measurements with other known systems, with other known postulates, as they're called, we can create really complex systems. We can go ahead and really craft an image or a description of the entire world around us. There's one such person who did an extremely good job of this. In the year 300 BCE, we're talking 2,300 years ago, there's a gentleman by the name of Euclid, who was an he was an Egyptian of culture. He lived in Greece in a city called Alexandria. You might have heard of library. It kind of predates the library. Euclid decided to create a book in his book called The Elements. In your notes, The Elements is a fantastic book which goes ahead and describes basically all the rules of elementary geometry. We're talking about angle systems. We're talking about how to calculate a pyramid. It's Egyptian. It's Egypt. Pyramid equations are pretty important. He's talking about how to make calculations that help farmers. He's talking about calculations that allow you to track stars, dictate seasons. We're talking about like systematizing kind of human experience in a certain way. Really fascinating stuff. And he did this 2,300 years ago. His book, The Elements, was so popular, so accurate, even though he didn't write everything himself, he kind of like drew the biggest mixtape of all time. He sampled tons of people, Pythagorean, for instance, and other various mathematicians. But his book was so good that it's still used today. The geometry that we're learning the next 3 weeks, the geometry that you have learned in the past, it's all because of this fascinating book. The Elements is considered one of the most popular books of all time. It's considered the most influential textbook of all time, and quite possibly one of the most published books of all time. If you go down to the library, you can buy a copy of it today. It might not be the same exact one, but it's one of the hundreds or thousands of iterations that have come out and written kind of in his own same style. Euclid was amazing in that he was able to come up with all these different equations, package them in a nice way, explain them in a nice fluid manner, but then also come up with all the proofs associated with this field of mathematics. The guy literally took a book and decided to calculate everything around us. It's pretty fascinating. And that's what sticks out so much for me with geometry, is you can have an individual like Euclid who's 23 years old, and just using algebraic principles, he can go ahead and kind of calculate everything. It's really fascinating. What I'd like to do is over the next 3 weeks or so is try and get this information into your head, try and show you some of the cool stuff that I see associated with geometry. We're going to have it done in a nice fluid fashion, the way that I feel like we're going to be having it organized. It's going to be pretty quick. Most of our videos that we're going to be talking about some of these concepts are going to be about 10 minutes. They're going to be shorter than this one. And your total time in the class each day is going to be about 30 minutes in total. That's why I'm picking a couple minutes off from you today. The way that our class is going to be set up is we have Google Classroom. From there, you'll have a link to an Edpuzzle, which you may or may not be familiar with, but there's directions on how to set that up on the Google Classroom page. And since you're seeing this video as well too, all this stuff's posted to YouTube, but for me to actually see who completed what goes through Edpuzzle. Edpuzzle is also cool because I can ask you questions like the one at the end of this video and interact and see your responses. The other thing that we're going to be doing is through Google Classrooms, I'm going to be distributing questions to you in two different fashions. One fashion would be through a text document where you see like picture examples, go through, answer some questions, maybe about 10 for the whole day because we're going through quickly. Or it's going to be posted up on a website called Delta Math, which there's instructions in Google Classroom for you to how to complete that as well too. But Delta Math is a nice website. It allows you to basically go in, answer questions. If you get it wrong, it tells you actually how to fix it and how to go through it. And we're going to use it in our videos to kind of show you a bunch of different things. So that's it in terms of for me today. I really wanted to press upon you kind of the beauty that I see in the field of geometry. It's what drew me into math in general, is being able to kind of systematize everything around you. And I hope to kind of systematize to some extent your experience in summer geometry with me. If you have any questions, anything of concern, we're going to be having office hours multiple times a day. You can always, of course, text me or contact me by email, which my information's posted up on Google Classroom as well too. But that's it. Till next time, hope you stay safe. Hope to hear from all of you, especially all the new students that we have here today as well too. So feel free to contact me. Bye.